Okay, I'm back, and I want to explain why I knew that I made a mistake. So here's the problem that we just did, is we found our 95% confidence interval for the estimate of the population from this sample, and I found that my margin of error was 3.35 years. And then when I compared that to the previous problem, where I found my 90% confidence intervals, for that one, I found that my 90% confidence interval was 4.39 years, 4.40 years. And I got, I immediately knew that I did something wrong. And here's the reason that I knew I did something wrong. Because this margin of error is bigger than this margin of error down here. And I should have actually observed the opposite. So here's why. Here's my data. My 95% estimate is I'm going to find the area under the curve here is 2.5% of the area on the right, and 2.5% on the area on the left. Which means that this range right here is my 95% confidence interval. Right, it's the area under the curve that extends from this left-hand critical value up to this right-hand critical value. And the left-hand critical value goes to this side here, where there's only 2.5% of the data to the left of it, and 2.5% of the data to the right over here. Now for my 90% confidence interval, I now want to find some new critical value here, where now the area to the left of this curve can be 5% of the area. And this new critical value here, where the area to the right of this curve is 5% of the area. Which means that my confidence interval for 90% will only go for here. Okay, so I better find that I have a smaller confidence interval using I have a smaller range of values for this 90% confidence interval than I do for the 95% confidence interval. And I actually observed the opposite. I was seeing that I had a larger margin of error for this question than I did for this question. So I went back, and as often is the case, I looked at the wrong number on the Z table. So it turns out that my problem was in the first problem. So this is example 8.5. Let's go back to this one. So this was all right. I was looking for Z of where alpha is alpha over 2 is 0.05. And I copied down that this was 2.57 or 2.58. If you go and look in your table for the area being 0.05, you find that that area is true for Z equals 1.64 or 1.65. So, and the true one is probably between these two numbers, but it's right between these two numbers. So this is not 2.57. This is 1.64. And this is not 4.39. This is 2.806. Okay, so we found our mistake. This doesn't stay the same. That doesn't stay the same. This will be from 33.57 to 39.19 years. Okay, so my 90% confidence interval is between 33.6 and 39.2. And my 95% confidence interval is bigger. It's between 33 and 39.7, just like I expected. Okay, so let's move on from there. Okay, so what do we do in here? Whoa, video screen did not like that. We'll figure out colors eventually. Okay, so what we used in the first part of that question is that we needed the sample size to figure out the number of samples that we needed for figuring out the margin of error that we wanted. We used this formula, and I showed you where this formula comes from. And the last thing that I want to do is another example using the same data. Now I want to find a 90% confidence interval for the mean age of all people in the civilian labor force, but the population standard deviation is unknown. I want to figure out what the margin of error is now. So just to backtrack a smidge, it's good that I caught that mistake. So we're going to redo our 90% confidence interval estimate, only now we don't know this number. We don't know that the population standard deviation is 12.1. So we got with this data that our margin of error was 2.806 years. And now with the same confidence, we're going to use the t statistic instead of the z statistic to figure out a new margin of error. And I expect that my new margin of error using the t statistic will be larger than this 2.806 number. And the reason is because not knowing this true population standard deviation introduces a new element of uncertainty into my calculation. So I have more uncertainty, more error, which means that my margin of error should get to be a bigger number. Hopefully that becomes the case. Okay, so this is where it's nice that I've put this data into my calculator already. So here's my calculator. I'll go and look at my list. So there's my list. It's list 1 where all of the data is in. So I'll go to the stat and I'll calculate the one variable statistics. And I've already been here. I see that the mean is 36.38. And I see the standard deviation of this sample is 11.07. So 11.069 years. So actually, my sample standard deviation is a smaller number than my population standard deviation. So I'm going to take back what I previously said. Actually, I don't know to expect that my new margin of error will be bigger. And the reason is because my true population standard deviation had a bigger standard deviation than my sample standard deviation was. So I may well end up with a smaller margin of error from my sample than my population. And that is just the way that statistics goes sometimes. Okay. So when we're doing things with where the population standard deviation is unknown, the procedure is exactly the same as it has been for the z statistic. The only thing that is different is that now when we're looking at the confidence interval, instead of looking for z of alpha over 2, we're using a different table of t statistics, of t values, instead of the z values. And that new table is much easier to use, so the t statistic is a lot easier to look up. And then we are also using, instead of the population standard deviation, which we do not know, we are doing our best guess, which is that the population standard deviation should be the sample standard deviation. So we plug in the sample standard deviation here. Okay. Oops, I need that. So let's do this. So I'll have example. I want E, which is going to be this thing that we're plusing minusing. So that's going to be T of alpha over 2 times S over the square root of N. I want the margin of error with the T statistic. I know that the sample mean is 36.38 years. I know that my sample standard deviation is 11.09069 years. And I need one more thing in order to use the T statistics. which is that I need the degrees of freedom. Degrees of freedom is the number of samples minus 1. So that's going to be 49. I should also go ahead and write down what n is because I do need the number of samples. So I'll write that n is 50. Okay, so we're ready to calculate that E is T of alpha divided by 2. Come back up here. We are looking for a 90% confidence interval. So that is that we are looking for alpha is 1 minus 0.9. Alpha is 0.10, which means that T of alpha divided by 2 is T of 0.05, half 0.1. So T of 0.05, and I'll go ahead and just write what the degrees of freedom are. So df is 49, just so that I know everything that I need to know to look this up on the table, times the sample standard deviation, which is 11.069, divided by the square root of 50. Now we need to use our table. So here is the table of T statistic values. I've kind of cropped it to show the things that we are interested in. So the value of T alpha is up here, and I am looking for T of 0.05, and I'm going to follow this column all the way down to 49 degrees of freedom, and I see that this is 1.677. So 1.677 times 11.069 years divided by the square root of 50. I put that in my calculator. I get that is 2.625 years. Okay, so, and that's actually all that the question asked for. So the margin of error here is that E is 2.63 years. Of course, on any homework or test question, I would tell you how many digits to round to. I've just been rounding all of these examples in to two decimal places. So I'm kind of continuing to do that for consistency's sake, but I would tell you on a test or a homework how many decimal places I wanted in this. So the margin of error is 2.63 years. So just to recap, doing these problems using the T table is exactly the same procedure. We're just looking up the value of T now instead of the value of Z. Otherwise, everything else is